All right, let's do one more example. What we have here is now the integral of e to the 2x on the top, all divided by 1 plus e to the 2x on the bottom. So to figure out what's my f here and what's my u. Now, one of the things that I can sort of note right off the top is that when I take the derivative of 1 plus e to the 2x, I'm going to get twice e to the 2x. I mean, there's this factor of 2 there that's a bit confusing, but it sort of looks like the top here is related, it's off by a factor of 2, but it's related to the derivative of the bottom. So let me experiment with setting u to be that denominator. Okay, so how does that work? U is the 1 plus e to the 2x. Its derivative, as we said, was the twice e to the 2x dx. Well, if that's my u, what's my f? This looks like the function 1 divided by u times du, but we're off by this factor of 2. All right, so that's the u and the du. But what is going to be, in that case, the f? Now, if I think about this expression, the place where u occurs is on the denominator. So I think my f looks like 1 divided out by u. And if I set my f to be 1 over u, that means that the capital F, the antiderivative of the lowercase f, is just going to be the natural logarithm of the absolute value of u. Now, why is this the case? Well, if we take the derivative of the natural logarithm of the absolute value of u, we're going to get 1 divided by u. So indeed, capital F is an antiderivative of the lowercase of f. Okay, so now if I take what my expression is, notice how I'm going to relate it. So we have this integral we want to compute. But what I've done here is I've divided out by a 2, and I've multiplied by a 2. And I can multiply and divide by a 2, that's just multiplying by 1, that doesn't do anything. But the reason why I do it is because now when I've got this 2 on the top, even though it's canceled down here, 2e to the 2x dx, 2e to the 2x dx, that is just du. That is, what I have done is managed to write this as 1/2 the integral of 1 over u du. So we get the 1/2 that just comes along for the ride. The integral of 1 over u becomes a natural logarithm, and I evaluate it at u, where u is this 1 plus e to the 2x, and finally I add in the plus c. So that is going to be my general antiderivative to this funky expression. And it's worth noting that integration in general is actually quite a bit harder than differentiation. Most of these functions that you can combine with quotients and products and compositions and exponents of the elementary functions we've been talking about, e to the x and sine and polynomials, we can just apply our rules and take the derivatives of all of them. But the other way around is not quite so simple. Some integrands, when you take the integral of some functions, it's able to be done because it can be manipulated to look into one of these nice forms like we have here with the substitution rule. But that is in general not the case, and there's all sorts of integrals where we don't have a nice rule like this to be able to apply.